I want you to close your eyes for a second. Seriously, just for a moment. I want to transport you back to school, specifically to the chemistry lab.
Ah, practicals day. I can smell it already.
You can, right? The ceiling fans are whirring overhead, making that rhythmic clicking sound. There's that faint smell of chemicals in the air, a mix of sulfur and spirit.
And you're standing at your workbench wearing that white lab coat, which is probably a little too big for you.
It's always too big.
Yeah.
And the pressure is on. The external examiner is walking around, looking over everyone's shoulder.
Definitely. The pressure's huge.
So you're holding a test tube. Inside, you have this bright, vibrant orange liquid. It looks exactly like, say, orange juice, but please do not drink it. It's chromic acid.
Right.
Now, you take a dropper, and you add just a few drops of ethanol, your standard primary alcohol, into that orange liquid. You give it a little shake.
And this is the moment where chemistry stops being just equations on a page and, becomes something real.
Because instantly, like a magic trick, that bright orange color just vanishes. It swirls, it fades, and it turns into this murky, deep green.
Mm-hmm.
And then a smell hits you. It's not the spirit smell of the alcohol anymore. It's sharp, pungent. It almost stings your nose a little.
And that smell, that's the smell of success. Or, I guess, scientifically speaking, it's the smell of a chemical transformation.
Exactly. We didn't just mix liquids. We created a completely new family of compounds. We made an aldehyde.
Yes.
Hello, everyone, and welcome to another deep dive. Today, we're tackling a massive topic for all the Class 12 students listening out there. We're cracking open Unit 8, aldehydes, ketones, and carboxylic acids.
And specifically, we are zooming in on the preparation of aldehydes and ketones.
This is a huge one for the board exams, isn't it?
Oh, it's one of those topics that effectively decides your fate in the organic chemistry section. Unit 8 carries a heavy weightage. If you can master these preparation methods, you are basically building the foundation for the entire unit.
It's interesting you say foundation. When I was studying for my boards back in the day, I treated this purely like a memorization game.
The old rote learning method.
Yeah, you know the drill.
Yeah.
Reactant A plus reagent B gives product C. I just memorized that RCH2OH gives RCHO. I didn't really care how or why. I just wanted the marks.
And look, that's how most students survive, but it's not how they thrive. If you just memorize, you get stuck when the examiner twists the question in the board paper or, during the Viva.
Right.
The mission of this deep dive is to move past that.
Right.
We want to understand the logic.
The logic behind the magic trick in the test tube.
Precisely. Why do we care about this? Why does the NCERT textbook dedicate so many pages to this specific process? It really comes down to one single word. Control.
Control. In what sense?
Chemical control. Think about it. An alcohol is a very stable, happy molecule. To turn it into an aldehyde or a ketone, we have to destabilize it. We have to change it. But we have to do it precisely. If you're a chemist in a lab, or even a student doing a project, you need to know how to stop the reaction exactly where you want it.
So it's about not letting the reaction just run away from you.
Right. Imagine you're cooking, let's say you're caramelizing onions for a biryani. You want them golden brown and sweet. That is your target product.
Mm-hmm.
But if you leave them on high heat for 2 minutes too long, what happens?
They turn into burnt charcoal.
Yeah.
Totally bitter and useless.
That is exactly the risk here. In chemistry, if you cook a primary alcohol too long or with too much heat, you don't get an aldehyde. You overshoot the mark and end up with a carboxylic acid.
So the aldehyde is the golden onion and the acid is the burnt mess.
Well, the acid isn't burnt. It's a useful chemical too. But if your aim was to make an aldehyde, then yes, making an acid is a failure. It's an impurity. So understanding preparation is really about understanding how to apply the brakes.
Okay, I love that framing. It's not just making stuff, it's controlling the chaos. So let's unpack this. At the absolute simplest level, what's the zero-level explanation here?
At the simplest level, preparation is essentially controlled oxidation.
Controlled oxidation. Okay.
And the best way to visualize oxidation in organic chemistry is to think of it as a heist. We're stealing.
A heist? What are we stealing?
We are stripping hydrogen atoms. We are stealing electrons.
It sounds a bit aggressive.
Chemistry is often aggressive. Think of it as stripping electrons from an alcohol. We take an alcohol molecule, we introduce an oxidizing agent, which is our thief, and we rip hydrogen away to force a carbon-oxygen double bond to form.
So we're turning a lazy single CO bond into a high-energy CO double bond.
That's a great way to put it. Now, I want everyone listening to build a mental model. This is crucial.
Okay.
Visualize the alcohol molecule floating in front of you. First, Picture a primary alcohol. That's RCHOH. The carbon holding the oxygen has 2 hydrogens attached to it. It's a bit crowded.
Primary alcohol. Crowded. Got it.
When we strip electrons from that primary alcohol, we get an aldehyde, RCHO.
So primary goes to aldehyde.
Now, switch the image. Picture a secondary alcohol, RCHOHRR. Here, the carbon with the oxygen is sort of sandwiched in the middle of the chain.
Right, between 2 other carbons.
If we strip electrons from this one, we create a ketone, RCOR. The double bond forms right there in the middle.
Okay, so the location of the OH group determines the product. If it's at the end primary, you get an aldehyde. If it's in the middle secondary, you get a ketone.
Spot on. And the goal, as we said, is to do this stripping process without destroying the molecule, especially with aldehydes. Aldehydes are fragile, they're slippery.
You mentioned stripping electrons. I feel like oxidation is a word students hear 1,000 times, but maybe don't really visualize. What's the oxidizing agent really doing at the particle level?
This is the deep dive part. What's really happening is that oxidation involves breaking a very specific bond. It requires breaking the CH bond that is directly next to the OH group.
The CH bond on the same carbon that holds the oxygen.
Yes. We call that the alpha hydrogen. The oxidizing agent comes in, grabs that hydrogen, and steals its electrons. This forces the carbon and the oxygen to share more electrons to compensate, snapping them into a double bond.
So the hydrogen gets kicked out and the C-No get closer.
Exactly. And that mechanism is why the definitions matter. So here is your anchor definition for the exams. If you're writing a descriptive answer, you can say,
Okay, pen and paper ready.
aldehydes and ketones are prepared primarily by the controlled oxidation of primary and secondary alcohols, respectively, using selective oxidizing agents.
That sounds like a textbook perfect line. Controlled oxidation of primary and secondary alcohols. But wait, I see a gap. We have primary, we have secondary, but what about tertiary alcohol?
I was waiting for you to ask that.
Surely, by the pattern, tertiary alcohols must make something. Do they make, I don't know, superketones?
Superketones, I like that. But no, this is a classic misunderstanding trigger. It catches students every single year. They assume tertiary follows the pattern, but actually, under these conditions,
Yes.
tertiary alcohols produce no reaction.
Zero. Nothing happens.
Nothing. The solution stays orange. No oxidation occurs.
But why are they so stubborn?
It's all about that mechanism we just discussed. Remember I said oxidation requires breaking the CH bond on the carbon with the OH group?
Yes, the alpha hydrogen.
Well, picture a tertiary alcohol. The carbon holding the OH is attached to 3 other carbons.
Right. RCR.
Look at that central carbon. Does it have a hydrogen attached to it?
No. It's bonded to 3 carbons and 1 oxygen. There's no hydrogen on it.
Exactly. There is no handle for the oxidizing agent to grab. There is no CH bond to break.
Oh, that is
Yeah.
a light bulb moment. So it's not that the region is weak, it's that the molecule itself doesn't have the right keyhole.
Perfectly put. No alpha hydrogen means no oxidation. So for this topic, tertiary alcohols equals no reaction.
That is a key takeaway. If you see that in a board exam, don't get tricked.
Just write no reaction and move on.
Okay, we have the mechanism, we have the no reaction rule, but I want to go back to this idea of control. How do chemists actually manage this?
We rely on tools, on the specific choice of the oxidizing agent. Think of it like selectively removing layers of a protective coating.
Like peeling a fruit.
Yes, let's go with that. A primary alcohol is a fruit with many layers of skin.
Okay, thick skin.
Now, you have 2 types of peelers, a mild agent and a strong agent.
Let's name them.
Our mild agent is the famous PCC,
PCC. That stands for?
pyridinium chlorochromate.
Yeah.
But for our analogy, think of PCC as a gentle, precise peeler. It removes just the outer layer of the primary alcohol.
And when you remove just that first layer,
You reveal the aldehyde, and crucially, PCC stops there. It gives you the aldehyde and walks away.
so PCC is the scalpel, it gives us the aldehyde.
Correct. But then you have the strong agents. These are the heavy hitters like potassium permanganate, KMNO. These aren't peelers, they're sandblasters.
Cam blasters. Okay, that sounds destructive.
It is. If you use KMNO on a primary alcohol, it doesn't stop at the first layer. It rips through everything. It oxidizes the alcohol to an aldehyde and then immediately oxidizes that aldehyde into a carboxylic acid.
So it destroys the middle step before you can even catch it?
Exactly. That's over-oxidation. So if your question asks for an aldehyde and you write KMNO as the reagent,
I get 0 marks.
you get 0 marks because you made an acid, not an aldehyde.
That is a crucial distinction. What about our secondary alcohols?
Secondary alcohols are much easier. In our fruit analogy, a secondary alcohol is like a fruit that only has one layer to peel.
Just one.
Structurally, yes. Once you remove that layer, you get a ketone. And ketones are tough. They are very resistant to further oxidation. So you can use PCC, you can use a strong agent. It almost always stops at the ketone.
So primary alcohols are the high-maintenance ones where the reagent choice is everything.
You've got it. And this entire concept, the invention of reagents like PCC, was a revolution in chemistry.
It sounds like it. What problem did this actually solve?
The problem of precision. Before agents like PCC, chemists really struggled. They'd try to make aldehydes, but the strong agents would just burn everything straight to acid. PCC allowed chemists to say, I want to stop exactly here.
It's cool to think that someone had to invent that specifically to solve this problem.
Exactly. It's a tool designed for a specific job.
Okay, let's lock this in with a mental movie. I want to put everyone back in that lab.
Let's set the scene.
You're at the workbench. 3 bottles of alcohol. A, B, and C. You don't know which is which. Next to them, you have a bottle of that beautiful, bright, orange oxidizing agent.
Okay, the orange liquid is our detector.
Right. Scene 1. You take bottle A, you add the orange liquid. As the drops hit, the orange color starts to fade, it swirls, and boom, the solution turns a deep green.
Green means reaction. Oxidation has happened, so bottle A is either primary or secondary.
Scene 2. You take bottle B, you add the orange liquid. Again, it swirls and turns green.
Another reaction. So bottle B is also either a primary or secondary alcohol?
Now, scene 3. The mystery bottle C. You add the orange liquid. You watch. You wait. You shake the tube. The color stays bright orange.
Nothing happens. The chromium has not been reduced. That tells you immediately. Bottle C is the tertiary alcohol.
That color change orange KRSI to green Cray3 is the visible proof of electrons moving.
Yes. Green means the heist was successful. Orange means the heist failed.
Let's connect this back to the real world. That ethanol example we started with.
Right. Ethanol, a primary alcohol, gets oxidized to acetaldehyde, that pungent smell. That is the aldehyde.
But there's a warning here, isn't there?
A huge one. If you leave a bottle of wine open too long, what happens?
It tastes sour. It starts tasting like vinegar.
Exactly. Ethanol, the alcohol, oxidizes in the air to acetaldehyde, and then further oxidizes to acetic acid. Vinegar is dilute acetic acid.
So you start with a nice wine, and you end up with salad dressing.
That is uncontrolled oxidation in the real world.
Now imagine the stakes in industry. Let's talk about pharmaceutical companies.
Okay, big pharma.
They are making complex drugs. Often, the structure of that drug needs an aldehyde group at a specific position to build the next part of the molecule.
So they need that aldehyde intermediate?
They need it desperately. If they use a strong, sloppy agent, the whole batch turns into carboxylic acid. The drug won't work.
And that's millions of rupees down the drain.
Millions. So when they use reagents like PCC, it's about economic and chemical efficiency. Control is everything.
That really puts the class 12 marks into perspective, doesn't it?
Absolutely. Now, I want to revisit one thing, that naive assumption about tertiary alcohols.
The superketone idea.
Yeah. Is there any way to force them to react?
Well, you can destroy a tertiary alcohol
Yeah.
with a very strong agent, high heat, acidic conditions. You can break the molecule apart.
But you won't get a ketone.
No, you'll get a mess, a mixture of smaller carboxylic acids. For the context of preparation, making a specific, useful product, it's a total failure. That is why we stick to the rule. No hydrogen, no oxidation.
Precisely. Okay, let's get ready for the exams. We need the exam safe clarity lines.
Yes, let's condense this. If you have a notebook, write these down. These are your golden rules.
Let's hear them.
Rule number 1. Primary alcohols plus a mild agent like PCC gives you aldehydes.
PCC equals aldehyde. Got it. This prevents overoxidation.
Rule number 2. Primary alcohols plus a strong agent like KMNOO gives you carboxylic acids. Do not confuse this.
Strong agent equals acid. That's the sandblaster.
Rule number 3. Secondary alcohols give you ketones. This works with both mild and strong agents.
Secondary equals ketone. Simple.
Rule number 4. Tertiary alcohols give no reaction under these conditions because they lack that alpha hydrogen.
Don't force it.
And finally, rule number 5. The observation. The color change from orange to green indicates oxidation is happening. This is your lab proof.
Those are gold. If you just remember those 5 rules, you are set for most questions on this topic.
Absolutely. Categorize the alcohol first, then look at the reagent.
So let's wrap this up with a short summary.
Okay, we started with the core idea. Preparation is controlled oxidation.
A hydrogen heist.
We visualize this with the 3 bottles mental movie. Green means go for primary and secondary. Orange stays for tertiary.
And the key distinction, PCC is your best friend for stopping at aldehydes.
And structurally, no hydrogen on that carbon, no oxidation.
Okay.
Before we sign off, I have a final thought for our listeners.
Let's hear it.
Think about the fragility of aldehydes. They're the halfway point between alcohols and acids. In a way, an aldehyde represents a state of chemical discipline. It wants to become an acid. Keeping it as an aldehyde requires precision.
That's deep. It's like keeping focus during exam prep. It takes energy to stay in that zone without burning out.
Exactly. Chemical discipline and student discipline,
Yeah.
same thing.
I love it. Well, there you have it. Next time you see a reaction question, visualize that orange to green change, smell the aldehyde, be the chemist.
And keep studying smart.
Happy studying.